All right, welcome back. So let's go ahead and work through some examples for the limits on infinity. Just like we've done for the rest of this chapter, we are going to look at evaluating the limits at infinity when we're looking at a graph, as well as doing some algebraically as well. So the first thing for the graph, it's, as we've kind of already talked about with the limits at infinity, we're really just kind of looking at the end behavior. Like, where is this graphing? Where is this graph going? As x approaches infinity, which as it's going to the right, like, where is the graph going? Now, if we look at this first example, we say, well, as we keep on going to the right, the graph stops, right? It doesn't go past this point. So therefore, there is no end behavior. And therefore, we can say that as the graph is approaching infinity, the function is not approaching anything as well. So this is non-existent, or we could say the limit does not exist. As we're approaching to the negative infinity, that means as we're going farther and farther left, you can see it's going to be approaching this horizontal asymptote, right? And therefore, we can say this horizontal asymptote is going to be at 1. All right, working into the next function here, g of x. Again, we have another endpoint here. But then looks like we have some oscillating, but the oscillating keeps on dampering down and looks like it's going to be approaching again another horizontal asymptote. So even though this is alternating, it's getting smaller and smaller and actually approaching the horizontal asymptote, which as we're going to the right towards in positive infinity is going to be a -2. But again, as you can see to the left, you can see that it is not approaching this asymptote. So again, this is another example of does not exist. All right, in this example, as we're approaching to infinity, you can see that this is going straight down, right? It's going all the way down. So therefore, this is going to be approaching negative infinity. As x is approaching negative infinity, what we can see here is we're actually bouncing between these two values of 3 and -3. Now, I didn't do the best job of drawing here, but what I want you to see is what we have is this kind of repeating pattern. It's going to go up to 3 and down to -3. So since it's repeating, it's actually not approaching an actual finite value. So again, this would be another example of the limit that does not exist, or a non-existent limit. All right, when we're looking at evaluating the limits algebraically, really what we're looking at is, what is this end behavior? Where is this graph going? So it's really helpful to kind of know, what the heck? Oh, that's supposed to be cubed. It's really helpful to kind of know what the behavior is of the graph, and to kind of know, where is it going for positive as well as for negative values. So in this first example, hopefully you recognize that this is a polynomial. And typically when we have polynomials and we want to identify the end behavior, we want to write them in our standard form. So this would be a 2x cubed minus 5x squared plus 3x. Okay. Now, I don't need to know exactly what this graph looks like. All I need to know, though, is that my first term is positive and my degree is odd. So therefore, this graph is going to have an end behavior that falls to the left and rises to the right. I don't need to know what the graph looks like, right? I don't know what that graph looks like. All I'm looking at is the end behavior. So as we're going to the right for this polynomial, we know that we're going to be going up to infinity. So that would be positive infinity. And as we're going farther and farther to the left, this graph is going to fall. So this would be to negative infinity. The next one is going to be a square root curve. Recognize that we have a negative inside of the function, so therefore that's going to reflect it about the y-axis. The 2 and the 3, all they're really doing is stretching and compressing the graph, so they're really not going to impact my end behavior, at all of my function. So the main thing I need to know is this graph is going to look something like that. Okay, square root curve, but it's going to the left, not going to the right, because it's being reflected about the y-axis. So as we're going to infinity, you can see that this graph stops, right? So again, this is going to be an example of does not exist. As we're going to the left, you can see that this graph is going up to positive infinity. All right, so next thing is when we're looking for rational expressions or rational functions, what we basically want to be doing is looking at the horizontal asymptote test. And we can look into doing some graphing techniques, seeing if anything would be dividing out. But in reality, no matter if we have holes or whatever else, if we have horizontal asymptotes, that's what the graph is going to approach as we're going to the left as well as to the right. So what I recognize here is whenever the denominator is larger than the degree in the numerator, we know that I'm going to have a horizontal asymptote of y is equal to 0. So this graph, no matter what's going on, again, who knows what this graph is going to look like? Who knows if there's holes or if there's where the vertical asymptotes are? It doesn't really matter, because as this graph keeps on expanding to the left and to the right, we know it's going to be approaching 0, because that's what the horizontal asymptote is. All right, in our next set of equation, we have 2x squared minus 9 divided by 3x squared plus 9. Again, recognizing the horizontal asymptote here. The horizontal asymptote is y equals leading coefficient over leading coefficient. The reason why I know that is because the degrees of both polynomials in the numerator and the denominator are the same. So when that is the case, it's just coefficient over coefficient. So therefore, this is going to be a 2/3, and this would be a 2/3. All right, next example, we have our degree in our numerator is larger than our degree in our denominator. So in this case, all right, so now let's go and get into some trigonometric functions. I don't really have to go very far with this one because I already recognize sine is going to be a graph that's going to keep on repeating, right? It doesn't matter if it's being reflected. It doesn't matter if it's being shifted, right? What we know is this graph is going to keep on bouncing, right? It's going to keep on repeating itself. So therefore, this is an example of does not exist and does not exist. Now, this next example, it looks very similar. A lot of people are like, oh, well, if sine is repeating here, then this one's going to be does not exist. But it's very important that we know the difference between this function and this function. This graph is going to be look a little bit different, all right? It's actually being shifted 1 unit to the left. And we've kind of talked about this graph a little bit before. And what happens here is it actually dampers down to a horizontal asymptote of 0. So in this case, as we're approaching infinity to the right as well as to the left, we're going to be going to 0 as well as into 0. So it's important to know the difference for this function compared to just a regular old sine function. All right, now this next example, typically I give my students a graphing calculator and they could be able to figure this one out, but let's pretend again that we maybe don't have any idea of what this graph looks like. So what we might want to do is kind of look at two different graphs. First, let's graph the radicand, x squared minus 1. Okay, so that's going to go from there. That's going to have two y-intercepts here, or x-intercepts, I'm sorry, and it's going to look like this. Okay, now again, it's very important for us to understand that this is whenever this is negative, right, between -1 and 1, that's not going to be within domain, right? Because any time between -1 and 1, for instance, 0, right? 0 minus 1, 0 squared is 0, minus 1 is going to be -1. You can't take the square root of -1. So we're basically looking for values between -1 out here and +1, all right? Now, let's just take a look at, let's just take a look at 3. Okay, if I plug 3 or a -3, right, what that's going to do is that's going to be 9 minus 1 is 8, square root of 8, 2.8, 284, 271, something like that. And what happens is, though, you have a negative on the back. So what this graph actually looks like is it's going to be from -1 to 1, and it's going to look like two square root curves going like this. But now that it's negative, it's just going to be reflected. That's just going to reflect the graph about the x-axis. So you can see this graph is actually approaching negative infinity from the right as well as we're going to negative infinity in the left. So there you go, ladies and gentlemen. Those are the examples to help you evaluate the limit at infinity. Go ahead and give some practice into the homework, and I look forward to seeing you in the next video. Cheers.